In the rotational dynamic, let us see the characteristics of circular motion. It is an accelerated motion, that is, as the direction of velocity changes at every point, it is an accelerated motion, as well as it is a periodic motion. So during its motion, particle repeats its path along the same trajectory. Thus, it is also called as a periodic motion. In circular motion, let us see some terms. One is position vector. Position vector is that vector drawn from the center of a circular path to the position of a particle, and it is also called as a radius vector. So here we can see the vector drawn from point O to the A, that is a position vector, as well as the vector drawn from the O to B, this is also a position vector. So the examples of position vector is nothing but the vector OA at time t1 and the vector OB at time t2. Now let us see the second term in circular motion is angular displacement. Here let us consider the position of a particle at point A at t time is equal to 0. This is the initial position of a particle. So B is a final position of a particle after a time interval t. Then this d theta will be considered as an angular displacement in time duration time t. Here the r is the radius of a circle, s is the arc of AB. Now when the particle completes a one revolution, that time the angular displacement will be considered as a 360 degree or 2 pi radian. So by definition, I can just take it here. The theta is nothing but the arc length upon radius, that is s upon r. So arc length, that is a linear displacement, can be written as r into theta. So this theta is nothing but the angle which is traced by this radius vector in time duration delta t. And therefore delta theta, that is a angular displacement, is given by delta s upon r, or delta s can be given by the delta theta into radius vector r. So we can define the angular displacement as it is a angle stress or described by the radius vector when a particle moves from one point to another in a circular motion, or it is an angle between two radius vectors. So it is always given by a letter d theta. Its SI unit is radian and it is a dimensionless, as well as it is a vector quantity. Direction of angular displacement is perpendicular to the plane of motion, and it is given by right hand thumb rule. It states that hold the fingers of right hand such that the thumb is outstretched and other fingers are curled. If the curled fingers denotes the plane of motion, then outstretched thumb points the direction of angular displacement. That is, the particle is moving anticlockwise direction. D theta is an angular displacement. The angular displacement is perpendicular to the plane of circle and pointing upwards direction. So if the particle moves in an anticlockwise direction, d theta is an angular displacement. The direction of angular displacement is upwards using the right hand thumb rule. Next term in circular motion is angular velocity. The rate at which angular displacement changes is called angular velocity. For infinitesimally small displacement, angular velocity is given by omega is equal to limit delta t tends to 0, that is nearer to the 0, vector delta theta upon delta t, that is equal to vector d theta upon dt. So this is a formula of angular velocity, that is angular velocity is equal to d theta upon dt. It is a vector quantity. Its SI unit is radian per second. Its dimension is L0, M0, T minus 1, and its direction is also given by right hand thumb rule. To know the direction of angular velocity, curl the fingers of right hand along the sense of rotation with thumb outstretched. The outstretched thumb gives the direction of angular velocity. That is, if the particle is performing anticlockwise direction, the curled fingers of a right hand is in the plane of a circular motion, then outstretched thumb is upward. So that is the direction of angular velocity is in upward direction. Whereas if the particle is performing a circular motion in a plane in a clockwise direction, then outstretched thumb is in downward direction. That shows that the direction of angular velocity is in downward direction. Next term in circular motion is angular acceleration. Consider the particle is performing circular motion in an anticlockwise direction. So as we see in the diagram, delta theta 1 and delta theta 2 is a change of this angular displacement. As the angular displacement changes, so its velocity also changes. So there is a change in angular velocity also. So average angular acceleration is defined as rate of change of angular velocity, and it is also represented by alpha. So by formula we can write alpha is equal to change in angular velocity upon time. So alpha is equal to vector omega minus vector omega naught upon t minus t naught. Here omega is a final angular velocity, whereas omega 0 is an initial angular velocity, where t is a final time instant and t0 is a initial time instant, and therefore we can write alpha is equal to delta omega upon delta t. This is also a vector quantity. Its direction is given by right hand screw rule. Its SI unit is radian per second square and the dimension is L0, M0, T minus 2. Let us learn the relation between linear velocity and angular velocity. Here we will consider the object is performing a circular motion in an anticlockwise direction. Delta theta is an angular displacement. During this angular displacement, the particle cover a linear displacement is delta s. So, by definition, linear velocity is nothing but delta s upon delta t applied the limit t tends to 0, that is very nearer to the 0. By definition of angular displacement, we get the value is delta s upon r. So just substitute the value of the delta s in this given equation. So we can write linear velocity is equal to limit delta t tends to 0 r into delta theta upon delta t. So linear velocity is vector v is equal to vector r limit delta t tends to 0 vector delta theta upon delta t. So this term limit delta t tends to 0 of vector delta t theta upon delta t is nothing but d theta by dt. and that is nothing but the angular velocity omega, and therefore we can write down the relation between linear velocity and the angular velocity is nothing but linear velocity is equal to r into angular velocity. They all are a vector uh, quantity, so we can write down vector v is equal to vector r cross vector omega. Next term in circular motion is periodic time. Here we will consider the particle is performing a circular motion. So, the time taken by a particle performing a circular motion to complete one revolution is called as periodic time or period. The letter for the periodic time is nothing but capital P. Time taken by the particle performing a UCM, that is uniform circular motion, to travel a distance equal to circumference of a circle is called as periodic time. So here it completes the one revolution which is equal to the circumference of a circle. We know the formula for the periodic time, that is period is equal to circumference of a circle upon linear velocity. This formula is reframed from the definition of velocity, that is velocity is equal to distance upon time. The time is taken as a period, therefore we get the formula for the periodic time is equal to circumference of a circle upon linear velocity. Substitute the values of it. Period is nothing but the t, circumference of a circle is nothing but the 2 pi r, and linear velocity is v. So formula for the periodic time we can get it as t is equal to 2 pi r upon v. If you substitute the value of v as a r omega, then r terms will get cancelled out and we get the another formula for the periodic time is 2 pi upon omega. And also we know that the reciprocal of periodic time is nothing but frequency. Here I use a alphabet small n for the frequency. You can write the frequency as a f also. So frequency n is equal to, we can get the omega upon 2 pi, or if you substitute the value of omega, that is v upon r, then we can write down the n is equal to v upon 2 pi I. The same thing is written over here. Frequency is equal to reciprocal of periodic time. So frequency is equal to omega upon 2 pi, or n is equal to v upon 2 pi r. The SI unit of frequency is hertz. Frequency of revolution is defined as number of revolutions performed by a particle performing a uniform circular motion in a unit time. So if in a unit time the object performs 2 revolutions, then the frequency I can just write down as a 2. This is a table for the kinematic equations which are analogous to each other. So velocity is equal to u plus v upon omega. Here velocity is replaced by the angular velocity, and that is given by omega naught plus omega upon 2. Here omega naught is a initial angular velocity and omega is a final angular velocity. Similarly, we can get the acceleration, that is linear acceleration is equal to dv upon dt. So angular acceleration is d omega upon dt. Linear displacement is equal to v average into t, or ut plus half at square. The angular displacement is equal to angular velocity into t, or omega naught t plus half alpha t square. Here alpha is a angular acceleration, and this is the third kinematic equation, that is v square is equal to u square plus 2as in a translation motion. In a rotational motion we can write down omega square is equal to omega naught square plus 2 alpha theta. This is the kinematic circular motions, kinematics of the equations in a circular motion, how they are analogous to each other.